Okay, why don't you go ahead and start, Dave?
Okay, so thanks very much for the invitation to speak. I'm a happy and frequent user of VST, but I'm not going to be talking about anything related to VST. I'll talk about the first T in the VSTTE acronym, and I'll mention in passing a tool, but this is really going to be a theory talk about some theory that's been done in collaboration with various people listed here on the slide, and a shout out especially to Ramana Nagasamudram, my PhD student. So what the talk is about is reasoning about relational properties of programs. What I mean is things like this: C1 and C1 prime are two programs. They're pretty similar, and I argue that they're equivalent extensionally. And to talk about that more formally, let me first show you my notation for Hoare triples in the box here. So a red squiggly arrow pre and post condition rather than the usual curly brace notation for partial correctness assertions. And then for relational properties, we'll use something similar, but C1 bar C1 prime is saying there's a relationship between an execution of C1s and C1 primes given by pre-relation between the initial states. I'll use primed identifiers sometimes to mean the value of the variable x in the second of two states. So this says if the two runs agree initially on the value of x, then afterwards they will agree on the value of z. Since that z is what's written by this program, that's my claimed equivalence specification. And there are many such relational properties. This is going to be the termination insensitive form. So if they both terminate, then the final states are related, the simplest of the relational properties. Relational properties come up in all sorts of contexts, equivalence of programs, equivalence under some conditions of two versions of a piece of code, equivalence of the compiled versus the source program. Also self-relations like non-interference, two runs from low equivalent states end up in low equivalent states and so forth. So how do we do this? Well, informally, if I was a programmer looking over your shoulder and you said, oh, I committed this new version, I'd look at this code and say, yeah, it's mostly the same. Let's see. I can line up my thinking about the two programs so they both initialize z the same way. Then they're going to do this branch test. Well, if x and x prime are the same initially, then after the pair of initializations, we'll have that x and x prime are equal, but z and z prime equal that value too. At that point, the test conditions will be equivalent. So I only have to think about both of them doing the then branches or both of them doing the else branches. If they both do the then branch, well, since they agree on the value of z, then 2 times z is going to be the same as z plus z, right? So I'll get the same outcomes there, similar for the else branch. So relational Hoare logics have been created to make formal deductive systems for this kind of reasoning. Here's an example. This is an instance of the general rule for sequence. So I want to relate two sequences, and I'm going to do it by proving a relationship between the first two terms in the sequence, and then a relationship between the following two terms in that sequence. Just notice my little flashy thing disappeared, spotlight. So that's the rule, very straightforward rule, like the sequential composition rule in unary Hoare logic, but here it's a relational thing, and it's capturing that pattern of reasoning I just did. Similarly, there's a rule, here's the general rule for aligned conditionals. If the pre-relation we're interested in, here R, implies that the two executions will agree on the value of the test, and I'm relating two similarly structured programs. So E prime, C prime, D prime might be completely different code. So don't read too much into the primes here. It's just saying there's some code, they're both if then else's, but I know that the test conditions will be in agreement. So then it'll suffice to verify that the then branches satisfy the relation and the else branches satisfy the relation, right? Simple pattern that captures that reasoning we did informally. Here's another example so we can talk about loops. So I'm going to relate this program to itself. It's a program computing factorials, and I want to show if you run it twice and the second run's input value, which I'm referring to in the spec as x prime, is at least the first run's input value, then the output value z prime will be at least the first run's output value. And we're going to reason about this without paying any attention to what's being computed, the actual functionality here. So imagine instead of factorial that the program is doing something far more complicated, but I'm comparing two runs on the pre-assumption that the second run's x value is at least as big as the first run's. If we look at the initializations sort of simultaneously, after both runs have done their initializations, then we'll have this Q relationship about Y and Z in the two executions. Now, the second run is going to potentially run more times since its input is larger. But if we imagine iterations only on the right side, the second run's loop body being executed under the alignment condition, if you will, that its value for Y is strictly greater than the left value of Y, that's going to maintain Q, the relational loop invariant. Likewise, if they agree on the value of Y, simultaneously executing one iteration of the loop body will maintain Q. And that's the gist of my argument here. Formally, we can write down these three correctness judgments that the init code establishes Q, that if you execute the body on the right, align an execution of the body on the right with doing nothing on the left, under the precondition strengthened with what the Y prime being greater than X than Y, then afterwards our loop invariant will be maintained. Also simultaneous iterations on both sides where Y prime isn't strictly greater than Y, preserve Q as well. There's a proof rule that captures this due to Leonard actually, and I've specialized it here to the case where I don't need the third premise, which would be symmetric, that I'm executing one iteration on the left, but not on the right. And the idea is we identify conditions under which one or the other of these patterns should be applied. And then we check that the loop invariant implies these conditions are exhaustive, and therefore the reasoning here is adequate. I've considered all the cases because given the invariant, either the two runs agree on the value of the loop test, they both terminate immediately, or both can be iterated, or else the alignment guard condition under which I want to think about one-sided iterations holds. And that's this term here. Okay, so I showed you some proof rules that capture some patterns of reasoning in terms of aligning subcomputations and expressed in terms of aligning subprograms. Here's another proof of the same, for the same example, where I'm going to use another technique. I've written down here C0 prime, meaning a renamed copy of the program. And now this is ordinary Hoare logic written as a proof outline. So we're encoding two states as one using primed identifiers to refer to the second state. If I execute C0, then afterwards, by some unary functional correctness reasoning, I know Z is equal to X factorial. And that will still be true after executing the second program in sequence, since it doesn't touch the variables of the first. So afterwards, we'll know that Z prime is X prime factorial. And then finally, using some mathematics about factorials, we can conclude that Z prime is at least Z, right? Using the rule of consequence. So the upside of this is displayed here at the bottom of the slide. If you want a complete relational logic in the ordinary logician sense that true things are provable, all you need is one rule of relational reasoning. It's this one. It says to draw a relational judgment, draw a relational conclusion about two programs C and D, rename D so that you can stick it together with C in a way that the executions mimic pairs of executions, interpret the pre and post relations as predicates, and do unary reasoning in Hoare logic. So if you have a complete Hoare logic and you have this one rule of relational reasoning, anything true will be provable. A bit weird, of course, because those other rules seemed kind of nice. They capture intuitively sensible patterns of reasoning after all. Also, those patterns of reasoning are crucially important if I want to do automation. The proof here on display is making use of nonlinear arithmetic. The proof previously here with the better alignment did no such thing. My loop invariant is very, very simple, more likely to be amenable to inference. But anyway, what about all this alignment stuff? This is looking sort of complicated now. And one consideration is ordinary Hoare logic gave rise to a commonplace in programming now. Developers use assertions, right? You write an assertion, some kind of notation that says, here's a comment in the code making a claim about all executions when control reaches this point. I could sort of do something similar. Here I've written down the products program, for our example, where I made renamed copies of the variables, and I've combined them in a way that captures the alignment that I wanted to reason about. It's not quite clear, though, where am I going to put that alignment guard condition that says under which conditions I want to think about just right side executions versus think about lockstep executions of the loop bodies. I also need to deal with encoding two heaps in one state. Priming the variables doesn't really work for memory cells and so forth. And once I start playing games like this, how do I justify that what I'm doing is actually an adequate way of proving the original judgment about the original pair of programs? I want to draw a conclusion in the end, and I would like a foundationally justified chain of reasoning all the way down to concluding the two programs are related, though in the meantime, in the interim, I had reasoned about some kind of hybrid thing. So the point of the talk is explorations in understanding how we might structure some stuff. So one notation one might consider And one representation is some kind of automata. So use the control flow graph. This is very popular in unary verification, after all. We can make a product of two automata, and we can augment such a product with some kind of conditions to indicate under what conditions I want to consider this product to be taking steps on just one side or the other. You could imagine such conditions could let me encode all sorts of alignments. That representation has, as a transition system of the combined two programs, has some virtues. When I give this talk at MFPS, I'll be followed by Hiroshi Uno talking about using constraint solving to actually solve for the alignment conditions simultaneously for solving for the relational invariance. So that's beautiful work, though limited to domains like linear arithmetic programs where we can do this kind of solving automatically. Another possibility that I've spent a fair bit of time on is making an ad hoc, a custom relational program logic for the language of interest. We're focusing on reasoning about the heap without separation logic, though borrowing the ideas very heavily, encoding them in ordinary first order logic. And we have a custom notion of biprograms. Here's the biprogram that represents executing C on the left, C prime on the right, with no a priori. And now the C prime here is any other program, not a renamed copy. No a priori alignment except at the beginning and end. Here's our notation for a method call where we want an aligned pair of method calls that signals in the proof system that we should make use of a relational spec of the procedure rather than a unary spec. We have other custom notations and so forth. The semantics is traces of state pairs. So during the computations, the semantics directly encodes alignments of individual steps. And our proof system accounts for the use of different alignments through an auxiliary relation. So if you're relating a sequence, C followed by D, with another pair of programs, C prime and D prime, that are also a sequence, you could weave them together. So there's this notion of changing the biprogram, relating it to another biprogram, and some rules that justify when can you do that. In that setting, we're considering fault avoiding semantics. So adequacy is a little less trivial than in the most of the talk today. I'll just talk about pure partial correctness and relational semantics. So we have all this custom stuff and we've worked it out in great detail. That's nice, but the literature is full of a lot of activity on relational verification and many different takes on how to represent aligned programs or aligned sets of executions and so forth. Well, if we're talking about automata and we're talking about algebra, and it's even Steve Bloom's birthday today, so we should be talking about algebraic descriptions of iteration patterns and so forth. I'm going to pick Dexter Cozen's take on this, the program algebra known as Kleene algebra with tests. So a cat is an algebraic structure two-sorted. So the sort B is meant to be a subset. These operations make an idempotent semi-ring plus the Kleene star operation with induction reasoning. And the set B is closed under these operations, and it forms a Boolean algebra under these operations. This beautifully simple algebraic structure is enough to encode imperative programs. For example, the encoding of an if-then-else is, I want all the executions such that either E is true and we do C, or E is false and we do D. Plus is the non-deterministic choice or union operator. A loop is encoded by, well, I want all the computations which repeatedly find that the test is true and do C, and which end with the test being false, right? We can encode or triples. There's several different equations. Here's one of them. PC is at most PCQ. All the computations of C that started in P states are contained in the ones which also end in Q states. It's an equation. After all, the less than or equals is just derived from the plus operation. So that's Kleene algebra with tests, a way of a nice, robust way of modeling imperative programs. And what we're going to do is escalate to bicat with some very decorated symbols here in my notation, because I need to talk about two cats. A bicat is going to be a cat with two homomorphisms that embed the underlying cat. So think of the underlying cat as my semantic domain of programs. For example, binary relations on states or traces on states, typical models of cat. And then my bicat, the idea is it's going to be pairs of program observations or executions. And we're going to be able to embed an execution of the underlying program on the left paired with doing nothing on the right, or vice versa, do nothing on the left and pair it on the right. And we're going to add this one additional axiom, the left-right commuting law, that says if you've embedded X on the left and follow it by Y embedded on the right, it's exactly the same as Y on the right followed by X on the left. Here's a derived notation, the embedding of the C with D. It's just a notation for doing them in that sequence. Of course, the law says that the order of these two doesn't matter. Now, observe that if I consider in particular the embedding of some program A followed by B and the sequence CD on the other side, by definition, it's equal to this sequence. By these embeddings being homomorphisms, I can expand it to that. Now I can apply the left-right swap. And so I have sort of an interchange pattern here. And if I hack up back with the definitions, you see within the algebra, I've explained why this alignment is an allowed way of reasoning about these two original programs. So I've justified the adequacy, if you will. Models of this algebraic structure include relations over state pairs. So think of the pair of initial states paired with the final states, okay? And then the test conditions, I'm interested in binary relations as my specs, right? Relating two initial states or two final states. We'll lift them to a co-reflexive, meaning subsets of the identity on these pairs of things. Another kind of model is trace pairs. So just like cat, one model is a cat of traces, sets of traces, and we have all these operations on trace sets. We'll escalate to trace pairs. We can also do pair traces, so traces that actually model the pairs of states as they go through a computation in some aligned way. I'm going to skip these two topics, which are for the MFPS. Yes, so now getting back to that relational Hoare logic stuff that hopefully seemed kind of annoyingly ad hoc, here's the property we're interested in so far, the for all relational property. For all pairs of executions, one of C and one of D from R-related initial states, we reach, if they terminate, S-related final states. This is exactly expressed by that Hoare triple equation in cat, only now I've lifted it up to the bi-cat level. So instead of a single program, I have the embedded pair of programs CD. And I lifted I'm using the hat to indicate, take the binary relation R in this picture where the little sigmas and taus are states, lift it up to a co-reflexive. So we're doing relation algebra style encoding of this relation. So you can now, with this simple definition, do what Dexter did for unary Hoare logic, namely derive all the rules of Hoare logic and more, just using the algebraic encoding here. And we can do that. Here's an example at the bottom of the sort of reasoning that would come up if you're proving one of the loop laws in relational logic. So you're interested in the pattern that I've embedded a loop and a loop together on the left. So E prime and C prime now, they're not renamed, they're any other arbitrary program, but the two programs being related here are both loops. Well, I can prove that there's an expansion law into this form. Notice here we begin by repeatedly executing both loop bodies, followed by either executing just the left loop under the condition that the right one's test is false, or the other way around, and then finally ending up that both tests fail. All right, so that's trying to put relational logics on a bit more mathematically robust foundation. What about for all exist properties? As soon as your programs could be non-deterministic for some reason and in some sense, you'll need some, sorry?
Question.
Yep.
So what if the alignment you needed to prove weren't something that was statically derived like this? For example, in one, you're aligning two programs, it takes 2 iterations, 3 iterations, 4 iterations of the second program in order to align successive iteration of the first one.
So in the relational logic style, the reasoning principle is, besides having a relational loop invariant, you introduce test conditions. I have the case where I want to sometimes take iterations just on the right side. So I've introduced this condition, the relation that y on the left is less than y on the right. And under that condition, I want to verify that the loop invariant would be preserved. And likewise, if it's not the case, it better be preserved by a lockstep execution. So in other words, Leonard's idea was you introduce some conditions under which one or the other side of the loop is going to be executed. And in that way, you can encode patterns. So what we were seeing here was the sort of generic pattern. And this isn't enough. This law of bicat isn't sufficient to prove that most general relational rule. For that one, I need an even more complicated expansion law, but I use by tests, right? I can insert tests in different places and do that algebraically. That answer the question okay?
Yeah, so in other words, you're kind of transforming the program so that it has this dynamic.
Right. So I'm trying to put on a formal footing the kind of transformations that are done all the time in especially automated tools. You do tons of program rewriting to get it into SSA form or what have you. And very often that's not fully, it's part of the trust chain, but perhaps not part of the proof chain. Here I can make it part of the proof chain. I do these formal rewritings, and some of them may be just like pure unconditional control flow sort of stuff. That's the basic laws of CAT. Some of them may rely on the semantics of the primitives that I'm using to justify that I've covered all the cases in some sense, right? The meanings of the tests and the actions will come into play. So we can do that in the framework of the algebra, or for that matter, you could use the algebra to do the purely propositional reasoning and then a separate tool to justify something more subtle that would allow you to have a better expansion. So this expansion law here is just kind of a basic one to get off the ground, although I will note that some of the well-known published works, for example, the Cartesian Hoare logic of Ishildillig and company, or the modular product programs of Peter Muller and company. This is the most general pattern of loop they can really handle. Is you do lockstep, you insist on doing them at lockstep as long as you can, and then you can finish off on one side or the other. But of course, that's not adequate. You actually want to be able to have more conditions on exactly how you do the alignment, data-dependent conditions. And I'll be coming back to that in a bit. But first, I want to talk about for all exist properties, because if the programs are non-deterministic, all I can hope for is that the set of outcomes may be related in an appropriate way. For example, for non-interference, I want to say that the set of given two low in publicly indistinguishable initial states, the set of possible outcomes from those two runs will be the same. Or put differently, we have turn off my phone, the usual forward simulation pattern that any execution from one of the states can be matched by an execution of the other state, leading to a final relationship, right? So this forward simulation pattern comes up in all sorts of contexts. So I like to be able to do the reasoning, and I like to do algebra. If Tony was here today, I'd be happy to point out I'm getting away from Hoare logic towards algebra. So here's one way to do it in just the calculus of relations, but that's not what I'm talking about today. In BiCAT, we have some projections which I glossed over, but they don't really work for this purpose. And what we can do, though, is the following. So there at the top is this pattern of reasoning I want to capture. Here, I've written it in a kind of weird way. And I was going to skip this part too. Yes, let me skip this. Okay, there's the pattern of reasoning I want to do. The idea is going to be, how do I prove this? Well, it's an existential. I need to show a witness, right? I need to show for every execution of C, there's some way that D could make its non-deterministic choices that would end up with the final states matching as desired, right? What would that witness look like? It needs to be making choices at the right points in time in a forward simulation or backward simulation way with prophecy or history as you like. And what we can do in BiCAT is insert intermediate tests, rearrange the program to line things up appropriately so that I can put a test in the right place that says the two runs are in agreement on some non-deterministically chosen values. Well, so there's going to be some term W that's going to be my witness term, but for it, and what I need to prove about it is three things. One is the for all property, that if you run this witness that's capturing pair of computations under the pre-relation, its computations all end up with related. So it's sort of been determinized and ensures S afterwards. However, I can't just do this by any old piece of code. I need it to be over approximating C, which is what this second condition says. The witness needs to have covered all of the left executions, right? Because I'm claiming for any of them, they'll exist a right execution. And the witness needs to be under approximating D, because we're claiming at the end of the day that we have these D executions. So anything that W is doing on the right needs to be allowed by D. And that's what this third condition is. So with this criterion, using the BiCAT algebra, one can derive, that's my next slide. So by the way, there's a backward simulation story, which I won't go into. And using that criteria of witnesses, one can then derive rules for a logic of forward simulation. There don't seem to be many such logics spelled out in the literature, although it's sort of straightforward once you look at it. The judgments here, this is the for all exist judgments now, but for the sequence rule, for example, it looks just the same as the previous rules. Here's the rule for if then else with that guard. This is the rule that for the case of reasoning about if then else is where they'll both go down the then branch or both go down the else. Here's a simple rule of loops where you can align them in lockstep. And we can derive all these kind of rules and also rules for non-deterministic choice algebraically using the tools that I just showed you. So Iris, RELOC, based on Iris, is one of the relational logics in the literature. It has quite an abundance of interesting features, but distilled from it, one could probably find these simple kind of relational logic rules for forward simulation. I haven't really seen the logic of backward simulation, but we can do that too, because we have this backward simulation characterization in terms of witnesses. I want to move on, though, and talk now not about logics, but about their completeness. And to do that, I need to give you a quick tour of an idea that doesn't seem to be well known in the literature, which is the completeness of Hoare logic. We know it's complete in the sense that true things are provable, but there's a stronger condition. So think about Floyd's inductive assertion method. It applies to the program control flow graph, right? The idea is, so here's my example program as a control flow automaton or graph. An annotation assigns assertions to each control point. The verification conditions require that if you start in a state that satisfies the starting annotation and run a bit of code to its ending point, the assertion at the endpoint will be valid, right? So if you have an annotated control flow graph whose verification conditions are true, then in fact the property will be true, assuming I annotated the precondition and postcondition at the beginning and end, right? So the theorem is that if I'm given a valid annotation for some correctness claim, then in fact I can prove it in Hoare logic. We knew that from Cook 74 about the completeness of Hoare logic, right? But we know more. I can prove it in a proof where the only judgments I'll be using are ones where the pre and post condition is directly read off the annotation. I don't need any assertions besides the ones that were in the annotation. Literally, that's not quite true. I need a few additional things like conjoining the loop test or the if test or its negation, but it's something very close to that. Intuitively, that's the rough idea. The proof is right there. I can follow that particular proof with that particular loop invariant in my Hoare logic proof. So I'm going to do the same thing then for relational logics. To get off the ground, let's think about one kind of product now encoded as an automata. So at the top is the program, its automaton, and here in blue is a product automaton acting on, so now I'm explicitly priming variables to indicate a second set of variables. And this automaton, if you look at it, it's starts at control point 1, and it basically does the execution of the left program first. And then eventually when the left program terminates, we start doing the execution of the right program. And we can annotate that using these factorial conditions and prove the correctness of the judgment we are after using this sequential automaton. So one can define what it is, a sequentially aligned automata, and any proof done using a sequentially aligned automaton like that can be proved using that one rule that I mentioned early on that says prove relational things by reducing them to Hoare triple unary reasoning in Hoare logic with a suitably encoded product program, if you will. And again, the proof, this will now be a proof in Hoare logic plus this sequential product rule. And in the proof, the judgments are going to be, again, the ones associated directly with the annotated automaton. So this is capturing that anything, thanks to this rule, any reasoning about a product representation, if the product is a sequential one, then I can capture it with this proof rule. If I've got other product representations, I might need other rules. So here's a program product that's doing, again, same problem, but we're now closely aligning the two executions. So my automaton states are pairs of control points of the original program. And when we're at point 1,1, we go to 2,2 by executing the initialization of y on both sides and so forth. Lots of lockstep stuff happening in this automaton. But the automaton has, as Shankar was asking about here, a data-dependent alignment conditions. Here's the one that says if y is not strictly less than y prime, we can fly right into the lockstep iteration of both loop bodies. If y is strictly less than y prime, then we can go off on this little detour circuit that's only executing on the right side. So this automaton is encoding alignments using data-dependent conditions. If you have an annotation whose verification conditions are valid for a product of that form, then the corresponding, then to get proof in a relational Hoare logic, you're going to need the conditional loop rule, the lockstep rules that I showed at the very beginning, and also one-sided rules to relate a command with skip. And the judgments now are going to be, again, things read off from the automaton where the pre and post relations are coming directly from the annotation. So, well, what about automata in general? I just showed you a couple of very particular alignment automata. So what to do in general? So this is unpublished work that we just worked out. Yes?
So question, go back to this rule reducing the aligned judgment to the sequential one. I mean, you're just making it harder to prove, right? I mean, truth be told.
Right. This is the terrible rule. The crazy thing is it's a logically complete rule, but it's a horrible rule because it says at the semicolon, you will need a complete functional correctness summary of your program. So you forget any, automated inference of invariance or anything like that. My example has just got linear arithmetic. In a more elaborate example, it would be even worse stuff. This is the worst way to align stuff. A programmer does not look over your shoulder and say, I'm going to imagine now the version you just committed and get all the way to its full computation, and then look at the previous version's full computations and align them, right? You don't do that. You do this simple idea that we did at the beginning, right? Think about step-by-step kind of lining them up in a neat way. And that's the point of these relational logic rules. And that's the point of alignment completeness, is to capture, well, does my logic faithfully represent all the different alignments you can think of? And our LIX paper had some particular ad hoc alignments, like if you do a sequential automaton, this is the only rule you need. If you're allowing yourself to do this very particular kind of conditionally aligned loops, well, then you'll get completeness if you have the conditionally aligned loop rule. And now I want to go on and wrap up with the idea that I've encoded my programs, I've got labels on my control point, so I can build automata out of them. I put the two automata together into some kind of a product with data-dependent conditions governing how it does aligned or unaligned executions. And now, what logic would be sufficient? So what I'm going to do is, first of all, switch notations for you. I'm switching to guarded command notation. This is now a do, but there's the arrow. And the normal form of my program looks like this. This is the instruction or automaton normal form of a program. It's got an explicit program counter. And depending on where the program counter is, you do the corresponding instruction and then update the program counter, right? So this is source code that's representing the behavior of a high-level machine, right? Should be a familiar idea. In fact, any command can be put into automaton normal form. So for any command whatsoever, I can put it into, there's a command hat that's in this very specific normal form, just has one loop doing all the instructions. It's provably equivalent using cat and a few axioms about the primitives to, well, not the original program, but to a program, because this new program is messing with the PC. What it's equivalent to is this program instrumented with ghost assignments, if you will, gratuitous assignments to the PC right in front of each control point, setting the PC to all these different values. The automata normal form, of course, is going to be messing with the PC in just that way. So it'll be equivalent. So I've got a normal form of a program, which is almost equivalent to the original modulo ghost stuff. And with that, and one more ingredient, I'm going to get completeness. The other ingredient, which is crucial for any kind of reasonable relational deductive system, is the rule that says, if you want to prove some judgment, relate, say, D to D prime, whatever they are, well, prove it for some better aligned, more convenient program, C and C prime, as long as that's justified. Well, how is it justified? C is equal to D, and C prime is equal to D prime. This is often implicit, like in verification tools, right? I SSA, formed my program, or I did some other rewriting, get desugaring and so forth. That's part of my trust chain, that when I verified the nice desugared program, it was actually telling me something about the original programs. So here I'm making that explicit as a proof rule. You could do that for unary, but this is the relational proof rule. And so the rule is sound as long as whatever equivalence notion you pick here is compatible with the meaning of the relational judgment. And here I'm picking a specific one, the cat provable equivalences. So now I get my alignment completeness result. So that's just a restatement of the rule at the top. A general alignment automaton is just a product automata where you can have whatever conditions you like, capturing the left, right, or joint steps of that machine. So suppose you have such a thing, and you have so you have an alignment product for the automata of two programs, C and C prime, and you have an annotation for which the verification conditions hold. Then there will be a proof. In what relational Hoare logic? Well, I need the Behringer's general loop rule that allows me to reason about loops, I'm going to be applying it to this loop. And I'm going to want to have one or both side executions of that loop. And what I'm going to be doing is using this invariant at the bottom that says, well, if the PC on the left is at I and on the right it's at J, then whatever the annotation tells me should be true. That's the relation that holds at that point. And so I will be able to get a proof if I have that conditionally aligned while loop rule, the lockstep rules, and a rule for elimination of ghost variables, right? I need that to justify this trick. I'm going to use the reason about the add PC version of my program in its automata normal form. And that's it. And I need the equivalence rule to justify that reasoning. So this is a theoretical result saying those are the only rules of relational Hoare logic you need. It is not a practical recommendation. I'm not saying you should do your verifications by always converting your program into the machine normal form. But in principle, that says we don't need to keep hunting for even more relational logic rules. So that's all I wanted to tell you about. I won't read the summary to you at the top. I'll mention some open questions like, how do we actually find a good equivalence relation in the setting of more complicated program models where you have the potential of divergence or faults and so forth. The algebra BICAT, we don't know very much about. In particular, we haven't proved equational completeness because we don't know what the free models are. And there are open problems about something called TRICAT that I didn't tell you about. Thanks.
Thank you very much. Questions from the audience?
Oh, and I meant to flash a slide with some related work. There's lots of work in this space, including at the top, the stuff on the relational region logic, where we're trying to reason about programs in a fragment of Java, actually has a tool. So I have the other T in VSTTE a wee bit. It's very much a proof of principle prototype tool, nothing like the very mature tools we've been hearing about in this very exciting workshop.
I've got a question about this. So could you go back to your previous slide? So I think this may be some motivation thing I don't understand. So long ago, we knew that self-composition, gave a bad but complete method for proving relational properties.
Right, right. In fact, Frances knew this in 1983, it seems.
And now you're finding some tighter condition to justify the rules that we wanted. Like there's some step I don't quite see.
So one thing I'm trying to do is to have a better understanding, right? Alignment is there in between the lines, in Aiken's compiler verification work and in all sorts of different work. In some works, it's explicit as a deductive system in Hoare logic. So I'd like to understand the science of this better, right? Somehow be more explicit about what alignment is about. And on that basis, maybe be more principled in coming up with deductive rules. So I showed you an algebraic way of making sense of the deductive rules. And also then the completeness part was about how do we calibrate, do we have enough deductive rules to capture the alignments that you might want? Since the sequential one by itself is complete in an uninteresting sense, but not adequate for practical use.
Okay, I guess the question is have you thought, are there any, maybe tighter notions of completeness that force you to have alignment rules and self-composition isn't enough?
Oh yeah, right. So I mean, self-composition is not complete for if you just allow in your repertoire alignments like this, where it's still very in our Lix paper where we talk about this in detail. It's still a very sort of specialized thing. Your program has to be aligned in lockstep, except that at a designated loop you can have this one-sided thing happening. So if you have automata of that form, you're not going to get completeness using just the sequential. You won't get alignment completeness using the sequential composition rule, right? Because alignment completeness requires that I've captured the alignment in the sense that I'm using only the assertions that are there, right? The sequential composition for my example forces me to do relational assertions involving multiplication. and factorial, right?
Yep.
I won't be able to do a Hort logic proof just using this sequential composition for that kind of alignment. I'm not sure if I've answered your question.
No, you did. Thank you.
So, David, another point here is that if you want to actually do this, reduce it to a more conventional form of verification, why don't you do the composition using scheduler?
You could. I mean, this general alignment automaton, you could think of as a scheduler, right? It's a little tricky in this domain because we're not talking about concurrent threads, right? This is conceptual. This is proving theorems by reasoning according to a certain pattern, but we want to capture the alignment, and it is indeed, in some sense, a scheduler. And people even use the terminology for that, right? Sometimes it's inferring the scheduling conditions.
Okay, so if there are no other questions, then we can release Dave to go off and give his second talk.
Yes, I'm going to run and do that, but it's been a great pleasure to be able to talk with you folks, and I'll be happy for feedback offline, and good luck in the rest of this very exciting meeting.
Yeah, all of you, we have future events, so, stay tuned and, please show up for.
Wonderful. Thanks
Thanks
again.
a lot, Dave.
Thanks to all the speakers and thanks to Leonard as well. Leonard, you want to say something?
I have nothing particular to say, just thanking everybody for showing up and being a very great audience, asking lots of questions. That's always useful in a workshop. Yeah, thank you very much, and enjoy the rest of your week.
Bye.